Moving on to question 2. So this question 2 starts off on the origin of color origin of color in transition metal complexes. So this question would have been familiar to many students trying to prepare for the A-level 9701 or in fact any other 16 to 18 years old chemistry exams. It's all about this origin of color or why are transition metal complexes colored. In this particular question, chromium complexes are colored because, well, chromium belong to transition metals because chromium has a partially filled d orbitals. Okay, so first of all, I think in the context of this question, I will say that chromium has a partially filled d orbitals has a partially filled d orbitals in most of its ions when forming complexes or when forming compounds. When forming complexes, or compounds. So this is just an additional point which I don't usually add onto my fixed essay, but I think it's quite relevant in the context that, you know, we are saying that there is a partially filled d orbital which are occupied has a partially filled d orbital with the d electrons in most of the ions and in most of the ions when they form complexes or the compounds. Let's get started with the main essay. So we know that we have the degenerate d orbitals. So I would probably draw this as some stage on the side, and I know they will be split into two energy levels in the presence of ligands. So this is Ml6 complex when it is octahedral, and this is just metal atom, no ligand. Okay, so in the context of chromium atom, it's got partially filled d orbital. When they form complexes in most of the ions, it will have partially filled d orbital as well. So both of them are rare in energy because of the repulsion that the ligands bring electrons with it, and that give covalent bonds to the metal atom that has got electrons in the d orbitals. So the repulsion causes the energy levels to go up in energy by a certain amount. I've seen in books as well, and I've done it in the past as well, where I don't show them going up, I just show them splitting like that. It's entirely acceptable as well because everything is relative as long as this is being split and they're no longer equal in energy, as the electrons in these orbitals repel differently to the electrons in this orbital with the incoming ligand. And this energy gap is characterized by delta, meaning difference in energy, equal to Planck constant times frequency of the radiation, which is going to be visible light radiation. So it's going to be hc over lambda absorb because, well, electromagnetic wave, which visible light belongs to, they travel at the speed of light, so c equal to f lambda. Anyway, so in terms of putting it into words, what can we say? We can say that the degenerate in the presence of ligands, or when ligands are present, then the previously degenerate d orbitals, degenerate mean the same energy, so the previously degenerate d orbitals get split into two sets of energy levels, 3 at the bottom, 2 on the top, 4 octahedral complex. This is an octahedral complex, Ml6, 2 sets of energy levels. So what can happen then is the electrons, I haven't mentioned about the energy gap yet. These energy levels are separated. These energy levels are separated by the energy gap. Delta E is equal to HF equal to HC over lambda absorb. Okay, so the electrons in the lower energy level can get promoted, or they can get excited. So promoted or excited to the higher energy level by absorbing visible light. So visible light refers to those light photons in the visible light region. By absorbing visible light, and you cannot occupy all those empty space in between. The electrons can only sit in orbitals, so they have to absorb a specific wavelength that corresponds to this energy gap as characterized by this equation. This is Planck constant, this is frequency of the radiation, this is speed of light, this is the lambda, meaning the wavelength of the visible light being absorbed. So what color do we see? The color of complexes seen will be complementary. The color complexes seen or observed is complementary. So there's a color wheel associated with this, actually complementary to that being absorbed by the complex. So whatever is being absorbed does not pass through. So whatever you see is a result or is a combination of whatever that passes through. Okay, so that's basically the fixed essay on these kind of questions. Typically speaking, we'll just start our essay from here and then just end here without this thing. I'm pretty sure if you don't fill this in, you will still get all the marks, because there are more than enough points in here that usually justify for why you get colors in transition method complexes, or the origin of color in transition method complexes there. Okay. Moving on to question 2, part B. So this looks like coordination chemistry. So this is very similar to one of the question that has appeared in previous papers. So what do we have? We have CrCl3 and then H2O6. We have CrCl3 and H2O5, CrCl3, H2O4. So it seems they are decreasing in that order. So there are more and more water molecules in there. And this is the mole of AgCl precipitated out per mole of complex. This is important information. In 1 mole of complex, how many mole of AgCl does it give off? Give off 3, give off 2, give off 1 and 1. So this is what you label P, Q, R and S. And then in terms of the shape, oh sorry, not shape, but is it polar or non-polar? I don't want to exactly copy down the question because again, there's a copyright issue. And again, well, you know where to find the paper yourself. I am not telling you where to find the paper. I am simply going through the tutorial as if you know where to find this particular paper. So what we can see is you give off 3 AgCl because what does this information tell you? That means there are 3 free Cl minus, there are 2 free Cl minus. Free in the sense that they are not coordinated. If they are not coordinated, that means they will precipitate out the AgCl. But if the Cl minus is bonded or dative covalent bond to the metal ion center, to the chromium center, that means they are not free. Okay, so the fact that they are free there would imply that the chromium has just got the H2O ligand. Out of the 3 Cl, only 2 are free. That means you've got 1 chloride on the chromium, which makes sense because 1 chloride is 1 monodentate, and you got 5 of the monodentate water. So altogether you still have octahedral complex with 6 dative covalent bond, but 1 of the chlorine. So in the complex, complex would be 1 times Cl minus and 5 times H2O. As a result of this information given, because there's 1 chloride, they are coordinated, whereas there is only 6 times H2O coordinated in the complex there. And there's 1 free chloride, so I have got 2 times Cl minus coordinated to the chlorine, and I have H2O times 4. So that is true for that. And these are the same scenario, so I can say they are the same. But what is different is one is polar and one is non-polar. As you can imagine, these are all octahedral complexes. Octahedral complexes they have bond angle of 90 degrees to each other. The fact that this is non-polar means that dipoles cancel out. As you can imagine, there's a symmetry. So we are looking at symmetry. And we have 2 times Cl minus and 4 times H2O. So you can imagine the 2 times Cl minus 180 degrees to each other. That's why they cancel out, and the 4 water is square planar in the middle of the plane. Let's get started with this question. So B part 1. Draw the 3-dimensional structure for P, Q, R, and S. So I already started by talking about the origin of why I know there are 6 water molecules. They want the complex ions. They don't want the free chloride or whatever. So they just want the complex ion. So if you have 3 free chloride, each of which is -1, and 3 times -1 is -3, this means this charge there is going to be +3 on the complex because the water has no charge whatsoever. If you got 2 free chloride, this is -1 times 2 is -2. So altogether, this complex remaining that has got 1 chloride and 5 water is going to be +2 overall. So that I'm talking about the charge on the complex. So be careful there. So I just want to highlight that very early on. So perhaps I can show P. So chromium there. So they haven't shown you the 3-dimensional thing at all. So I need to show these lines where these two are flat. These two are coming out towards you, coming out from the screen, from the paper. These two are away from you, behind the screen, behind the paper. So you can't draw them as just line because they are not flat at all. If I just copy these very quickly, because I don't want to have to draw them again and again. And they have given us R and S at the bottom as well. So R and S. Okay, so that's P, Q, R, and S. So remember what I said about P earlier? So 3 times free chloride, that means all the chloride are free. So there's 6 water around the complex. So we're looking at P being chromium, H2O6. So this is chromium 3 plus because you got 3 free chloride, each of which is -1. So I have OH2. OH2, remember, is the lone pair on the oxygen. The lone pair on the oxygen is the one with the electrons or the lone pair in order to form dative covalent bond. So do not show your arrow going to the space in between or to the hydrogen because the lone pair is on the oxygen to form that dative covalent bond. In Q, you have 2 free chlorides, so you have 1 chloride and 5 water on the complex. So you have 1 chloride and 5 water on the complex. So you still have 3 plus on the chromium, but you got -1, so overall it's 2 plus. That's why there's Cl minus and Cl minus. That's why there's 2 free chloride. That's why you get 2 mole of AgCl for 1 mole of this complex because there are 2 free chloride. So I just have 1 chloride which I can put anywhere. I'm just going to put my chloride on the axial rather than equatorial. It doesn't matter whatsoever. What is important is I need to try and get the charges right. So, I try to put in my charges on my complex all the time. What I can do now is I can draw for R and S. But R and S, similar concept, 1 free chloride means 2 of the chlorides are coordinating on the chromium. And I have 4 water, but one of them is polar and one of them is non-polar. I said earlier the dipoles cancel out for S because the chloride are 180 degrees to each other. So I can draw S first, where the dipoles cancel out. So the chloride are 180 degrees to each other. So CrCl2, H2O4, and that will be a plus now because +3, -1, leaving me 2 of the chloride. And then we fill the rest with the water. So remember, it's the oxygen with the dipole. It's the oxygen with the lone pair that will form dative covalent bond to this complex center. So we've got the overall charge of +1 there. And that will cancel out the dipoles because this dipole of the chloride, both are axial, so these cancel that, these cancel that, and these cancel that. So everything will lead you to this complex being non-polar. So this is what you call a trans because the chloride and the chloride are 180 degrees to each other, whereas here the chloride and the chloride are 90 degrees to each other. As you know, the bond angle in the octahedral geometry is all 90 degrees, including in the square planar equatorial position. They're all 90 degrees to each other, even though I've drawn this bit at the back a bit bigger, but they're all supposed to be 90 degrees square planar in the middle. But then these things are linear, so together you got 6 bond pair and 0 lone pair, octahedral 90 degrees. So here I could have put the chloride anyway, as long as the Cl and Cl are 90 degrees to each other, and I fill in the rest of the ligand space with just the monodentate water. I will also have a +1 complex again because this is also chromium with 2 chloride because I only have 1 free chloride because I only precipitated out 1 AgCl per the complex. I only give out 1 AgCl. That means 2 of my chloride are not free. They are bound onto the chromium. But this R is polar because the dipoles do not cancel each other out. So this is a polar complex. Whereas the one on the right hand side, complex S, the dipoles does get cancelled out. So that is the non-polar complex. This is cis, the other one is trans. So the trans one is the non-polar complex. So I hope that is quite clear there. Not too sure if I can make it a bit clearer. Perhaps I can draw a partition there. That seems better. Perhaps I can draw a partition there. That seems better. So it looks a bit neater because there are boxes in the question. They do say that draw three-dimensional diagram. So 2 out, 2 in, and 2 are flat. Include the charges for each complex ion. I included the charge already because there are 3 free chloride. Based on this information, there are 2 free chloride. So, you know, 1 is bound. So plus 3 minus 1 give you plus 2. Plus 3 minus 1 minus 1 give you plus 1 for the charges that I have included there. So on to the next question. So question 2b. Part 2, they say why S is non-polar. So I already mentioned it just now. S was the last one there because the chloride ligands, the chlorine and the chlorine there, are 180 degrees to each other because the two chloride ligands, the 2 Cl minus ligands are positioned trans, meaning 180 degrees to each other. Therefore, dipole cancel out. Therefore, symmetrical. So it has a symmetrical structure. As a result of the symmetry, their dipoles cancel out. When dipole cancel out, no overall dipole. Therefore, no overall dipole. It's a 1-mark question. I guess you can probably skip to the point and just take the most important information. They give us 2 lines. I've written more than 2 lines. The idea is about the trans geometry, symmetrical structure. The dipoles cancel out. That's why this molecule is non-polar. So this cancel that cancel that cancel that. Question 2, part C, this is about definition. So they want you to talk about this picolinic acid. So let me try and get that right first. That, and I have CO2H. So they call this picolinic acid. They say the conjugate base is a bidentate ligand. So this is a carboxylic acid. So when you deprotonate that, then it's a carboxylic acid, so it's going to be a weak acid, so it partially dissociates into the H plus ion. When it does that, then you will be left with something called carboxylate, something that look like this. This is a carboxylate. This is the conjugate base, and what they are saying is the conjugate base can be a bidentate ligand. Originally, we have a lone pair on the nitrogen there, and now we also have a lone pair on the oxygen that we can see there. So altogether, you have 2 sites, one like this and one like that, as your possible coordination site. So one molecule or one ion or one such species can form 2 dative covalent bonds to the transition metal or the metal ion center. So what is the definition of bidentate ligand? So there are 2 parts to this definition. What is bidentate and what is ligands? So bidentate ligand forms 2 dative covalent bonds. So very important. So 2 dative covalent bonds to metal ion or metal center per ligand molecule or per ligand ion. Okay, so this is an ion. So in one of these ions, it forms 2 dative covalent bonds per one single ion. So it's very important to mention that for one single ion, they form 2 dative covalent bonds. They have at least 2 species with 2 individual lone pairs. They can form 2 dative covalent bonds. If I were the examiner, I'll be looking at 2 dative covalent bonds. I'll be looking at per ligand molecule or per ligand ion, because it means in one ligand, how many dative covalent bonds do you form? Here, I've just shown you that. They are not asking you to do that, are they? Yes, they are. They do ask you to show the structure of Z. So, this kind of thing, they always follow one another. You do not need to show the dative covalent bond because they just want you to show the structure of Z. So that is Z, which is the conjugate base. Conjugate base is what you get after the acid donates the proton. After the acid donates the proton, you get something called conjugate base that's in your AS equilibrium under acid and bases. Okay, so what do we have? Z reacts with aqueous chromium 3 plus in a 3:1 ratio. Okay, so this is about coordination chemistry. So if I have Z, I have 3 of Z because it's a bidentate ligand. So 3 of Z plus what? Plus chromium H2O 6, 3 plus. So I will have 1 of these and I'll have 3 of that. And what I will get is I will expect to get chromium Z, 3 of Z. Each of Z has a -1 net charge. So if I have 3 of that, I will have, originally I have +3 charge because the water has 0 charge. So that's why overall is +3 oxidation state. So the chromium is still +3, but each of the Z is -1. So each of the Z is actually -1. But I have 3 of Z. So altogether, I have +3, cancel out -3, I will have 0 charge. Okay, so no charge at all. So I don't show the charge. Coordination number. Oops, I don't mean to do that. So remember, this is bidentate. Bidentate means 2 dative bond. 2 dative bond per ligand. So I have 3 of the bidentate. So 3 bidentate would mean 6 dative bond. I am really running out of space here, so what I'll do is I will copy all of these onto a new page so that I will not be hesitant to use more space if I have to. So 3 bidentate ligand would mean 6 dative covalent bond. 6 dative bond would mean coordination number is going to be 6. Okay, because coordination number is defined as the total number of dative bonds, dative covalent bond around the metal ion in the complex. You have 6 dative covalent bonds, even though you only have 3 bidentate ligands. Your geometry is going to be octahedral because they are still 16 around the complex. Okay, so octahedral complex, octahedral geometry, 6 coordination number, but only 3 bidentate ligand because each bidentate ligand form 2 dative covalent bond there. And the charge is going to be 0. They haven't asked you that, but the charge definitely cancel out because this is a -1 charge. When you have 3 bidentate, you have a -3 overall. Cancel out the chromium +3 because in this reaction, you also kick out 6H2O, by the way. This is simply what you call a ligand substitution. These are ligand substitution because you are replacing the monodentate water with this bidentate ligand Z, and this is not a redox. If it is not redox, that means the chromium +3 is still chromium +3 in the end. Part 4. So what we have, oops, sorry, not part 4, but part D. So this is question 2, part D. This is oxidation number. So we have this compound called ammonium dichromate. There are 2 ways of doing this. If I were you, I would be thinking about ammonium. Ammonium is NH4 plus. So NH4 plus, there are 2 of them. So therefore, we are looking at Cr2O7 2 minus, which of course we know from AS as part of a common oxidizing agent. This is called dichromate 6. If you know it straight away, then you should be able to get the oxidation number is +6. But if you don't, then you know the oxidation number of the ion is -2, following the revelation that you have 2 of these +1. So the balance is -2 to give you an overall compound with no charge. -2 equal to the oxidation state of chromium times 2 because I have 2 chromium, +7 times -2, 2 chromium equal to +14 -2. Chromium equal to +12/2, chromium is +6 there. As you know, dichromate 6, chromium +6. Without the plus, it's not going to make any sense at all. Cr2O3, overall compound has no charge, so oxidation number is 0. I've got 2 chromium, I've got 3 oxygen, each of which is -2. So 2 chromium is +6, chromium is +6/2, chromium is +3 in Cr2O3. Next up, what do they want us to do? They want us to write a balance equation for the decomposition of that. What I'll do is I'll move this up a little bit because I'm running out of space here. We can think about a redox equation in the context of change in oxidation number must be balanced out. Okay, that's probably the angle at which they want us to do this in. They will decompose to give you Cr2O3 plus H2O plus an inert colorless gas. Inert, first of all, is an inert. Inert means unreactive. So inert, colorless gas. The fact that it's inert would imply that it's N2. The fact that it's colorless would imply that it's not NO2. And it's not oxygen as well, because oxygen is not completely inert. NH3 is not inert. So we can be safe in confidence that it's got to be N2, because there's no nitrogen in here at all. There's only nitrogen left that I need to balance the equation. Anyway, so what do I have? I have chromium plus 3. I have chromium plus 6. And to think about the nitrogen as well, if I have the nitrogen, I think it's best if I actually move this onto a new page, because again, I don't want to be running out of space when I do this kind of question. So this is question 3, or was it question 2? It was question 2, so question 2 part D. And it's the last part to that. I'm trying to show the changes in oxidation number. So we remember that the nitrogen, they come from the NH4 plus. So the overall oxidation number NH4 plus is +1. The nitrogen is unknown. I have 4 times +1 hydrogen. So the nitrogen is +1 minus 4. Nitrogen is -3 there. What happened there is nitrogen 0. So what can I say? Nitrogen -3 to nitrogen 0 is an increase of 3. Whereas if I look at the blue one, chromium plus 6 to chromium plus 3 is a decrease of -3. Changes in oxidation number must be balanced. However, be careful, chromium is for 1 chromium. So I have 2 chromium there, which means I have 2 times plus 6, and I have 2 times plus 3. So altogether I have plus, what do I have actually? I have plus 12, I have plus 6 there. So altogether I have -6, to be honest. And here, nitrogen is for 1 nitrogen. I actually have 2 nitrogen. So actually I will have 2 times nitrogen -3. But I only have 1 times of that nitrogen 0. So again, that should be +6. But happily, my -6 will cancel out +6 as well. So, you know, very, very easily you get one of these. That should give you one of these, because 2 nitrogen and 2 nitrogen, 2 chromium and 2 chromium, 7 oxygen, 3 oxygen, so 4 oxygen. I need 4 more oxygen there, so it's got to be 4 there. And the hydrogen is 8. The hydrogen is 8. Everything is balanced, so you get a balanced equation just like that. If I just write it out neatly. So this equation, probably you don't need to use changes in oxidation number to balance this equation, because it should be quite easy to balance after all. But it's probably a lot easier if you just think about the oxidation number, no changes at all. Well, I mean, there's a change, but you know, they're balanced out. So in that regards, they become easy, because one of that, and one of that. So you're just balancing out the atoms, which is just from the water. So that's it for that 15-mark question number 2.